Good morning, everybody, and welcome to a Hamilton webinar. This is part of our Bioprocessing Excellence webinar series, and today we're going to be talking about total cell density reimagined. Now, usually we have a host and a moderator and a presenter. However, I will be doing both today. So my name is Jacob Crow. I am the Senior Application Specialist for Hamilton, PA in Reno, located in Reno, and I service the US as well as Asia territories. So to give you guys a little bit of background on what's going to happen for this presentation, I'll first present our topic today, and then we'll have a Q&A section immediately following this presentation. So if you have questions, please feel free to put them in the Q&A box at any given point in time. But I'll go through them at the end and try and address everybody's questions. So what are we talking about today? Well, I'll tell you a little bit about Hamilton Company, and then we're here specifically to talk about total cell density as a measuring principle, and then what Hamilton has in terms of a solution to try and improve this measurement within the process analytics field. So Hamilton at its core is a series of multiple business units. We have business units in laboratory analytics space, robotics, storage, medical, and process analytics. Now, process analytics is the field that I'm in, and that is typically, if you're in the biopharma space, going to be a technology you're probably most familiar with at the bioreactor scale. A little bit more about Hamilton. We're founded in California, and we're a privately held company. PA was a recent addition, and by recent I mean 1993 to the Hamilton portfolio, and we're a decent sized company with over 2,500 global employees throughout the world. So process analytics specifically, what do we provide? Well, we provide measuring solutions in terms of calibration, conductivity standards, but our main service and our main product portfolio consists of providing a complete measuring loop for sensors such as pH, or for measurement, for individual measurement parameters such as pH, dissolved oxygen, conductivity, carbon dioxide, VCD and TCD, which we'll be talking about TCD today, as well as ORP, and then all the accessory equipment, I'll call it accessory equipment, that goes along with making these measurement parameters within your process. Things such as housings, calibration solutions, cables, and transmitters. And so our goal is to provide every measurable parameter you'll need in the biopharma, industrial chem, industrial space. And since the late 80s, early 90s, we have kind of tried to be on the forefront in innovating. We started out with pH sensors, improving the glass formulation, as well as changing the overall pH sensor design. We introduced measurements into the dissolved oxygen space, specifically an optical dissolved oxygen sensor, as well as tried to undergo a paradigm shift in switching from a transmitter-based system to a sort of intelligent sensor technology. And I'll comment a little bit more on what I mean by that in this webinar. We also acquired online viable cell density measurement for VCD in process, as well as provided single-use solutions, not just pH, but we also have DO, conductivity, as well as VCD in the single-use format. And we don't just take a single technology, we try to successfully iterate on this. So our second generation Insight sensor called Dencytee Arc was released, as well as trying to devise novel inline measurements for critical process parameters, something like a CO2 sensor. And so we recently also released a solid state optical DO or optical CO2 sensor to the market. But that's not done, and we're not done, and that's why you are all here today. So today we're going to talk about total cell density and the Hamilton approach to total cell density, and how we want to address this measurement parameter. Before we talk about Hamilton's solution, let's talk about what is TCD. So total cell density, we define as measuring both living and dense cells, as well as cellular debris within a within a bioreactor or a bioprocess. Typically, it's calculated, and I'll say TCD and total cell density, those are interchangeable. Typically, it's calculated in an offline fashion. Cell dry weight and or an OD measurement and offline OD measurement are some of the two more common methods that total cell density is measured. Now, offline measurement has a lower initial investment cost. However, it's got high operating costs due to the fact that it requires labor, physically somebody in the lab to take a sample and make the measurement. As well, because it's a discrete measurement at a specific time point, and there's a certain amount of time required in order to make the measurement, we call it a delayed measurement. A certain window of time has passed. And so any action taken from this is still a reactive action. And what I mean by the time delay and the multiple steps required in this is, let's take this fermenter right here. If I want to get a sample to understand what is my TCD at any given point in time here, I have to first sterilize and then take a grab sample. I have to assume that grab sample is representative of the entire bioreactor itself. And then typically for things like UV-vis spectrophotometers, I have to dilute my sample down in order to be within the measurable range or specification of this of the UV-vis spectrophotometer. So, okay, I do that, I get a measurement. And that measurement is typically done by determining the amount of light that is deflected from a given incident source. And this in the bioprocess is typically going to be cells as well as cellular debris will contribute to the amount of light that passes through and is received on the detector end. And this is the basics of the measurement principle for offline UV-vis spectrophotometry. So let's say we take a measurement, we trust the value. Okay, we're going to go make a process action. Even if we're very much, this is our number one objective priority, there's still a certain amount of time delay here. And so this is what we mean by the amount of time it takes to take the sample. The fermentation has progressed beyond that point. So it's a very much a reactive approach and not a proactive approach. And Hamilton saw this as an advantage, or Hamilton saw this as a particular avenue for us to improve upon. And so we're in the business of making inline cell density measurements or inline measurements. And so the Hamilton solution was to go ahead and take this offline measurement and convert it to some inline format that can be continuously measured. Now, before I show you how we went about trying to solve this avenue for improvement, let's talk about why, or what are the advantages of this. TCD measurement, inline TCD measurement has distinct advantages that are present not just at, say, the R&D scale, but also through pilot and production. But I'm going to go ahead and delineate them out. So at the pilot or at the R&D scale, TCD, inline TCD measurements enable you to have process control capabilities or implement process control capabilities in what may have been historically limited to something like just grab samples and making a measurement. At the R&D scale, it's important to understand your process through and through. And so the Hamilton, our Hamilton inline TCD sensor provides a high precision fingerprint that gives you a complete picture of the entire run itself. And so from that, we say you can improve your process understanding. And as well, you don't need as many samples in order to know where you're at. We're not saying necessarily to get rid of offline sampling. Use it as a complementary tool to say, we have agreement in both our inline measurement as well as our offline measurement on where we are in terms of biomass growth, as well as where we are in terms of our fermentation sort of life cycle. At the pilot and production scale, all of these advantages translate, but you also have, when you start to look into the GMP space and you start to look into more quality aspects, you have the ability to detect deviations. As I'll show you on the specifications of our sensor, if you establish a guideline or fingerprint with our sensor, you can detect to a pretty high degree what is sort of out of specification versus what is in specification for a particular fermentation growth profile. To this, you can also improve things such as seeding, induction, and harvest point management. This goes aligned with sort of enabling process control, but also by having a high precision fingerprint, if you give a specific number, you can rest assured you're going to hit that number. Applying process control, as I kind of just mentioned. And then at the end of the day, you have a golden sort of a golden batch profile, specifically for GMP and production environments. You can look back in your batch records and say, yes, I have this this inline fingerprint that characterized the entire process for the TCD measurement. And then reduce sampling. So how does our sensor or our solution actually work, and why is it advantageous? So let's take the basic transmission measurement from the offline UV vis spectrophotometer, and let's put it in an inline sensor. And so what we see here is a depiction of a basic transmission-based sensor where you have on one end of this measuring path length, you have an emitter that emits a light source, and then a detector at the other end that detects the amount of light passed through. In the presence of cells, the amount of light passing through from the emitter to the detector is going to vary, and it's going to decrease as the amount of cell density increases. At a certain point in high cell density processes, almost no light is passing through to the detector, at which point you either need a incredibly precise detector or an incredibly sensitive detector. You need to increase your light source, or you need to dilute your sample within the window pane in order to get back within specification, kind of like with the offline UV vis spectrophotometer. You can't do that in process, so that's out. And really what you need is you need to either respecify the detector or come up with a different way to measure. And so what we did was we said at high cell densities, the amount of light reflected back to the emitter is going to be significant compared to the amount of light passed to the transmission detector. So why not use both measurements? And that's what we did. We combined in our new Dencytee Arc system, we combined a dual detector based system into our inline density measurement. And so here's the sensor itself. The sensor itself has a standard PG 13.5 connection. It'll fit into any pH or DO port that you have for any bioreactor, let's say 1 liter scale, all the way up to your 1,000, 10,000 liter fermenters. This is a standard sensor that falls along with your pH and your DO measurements. The sensor itself has both transmission and reflection, as I sort of mentioned there, as well as a temperature compensation system and a daylight filter and subtraction mechanism built into it as well, to ensure that the measurement you're getting is not dependent upon the ambient light that's passing through, say, your glass bioreactor. We make this sensor in lengths from 120 to 425 millimeters. This will satisfy any bioreactor scale that you really feasibly need this in, if it has a PG 13.5 connector. It's stainless steel to fit and conforms to all the regulations required in the biopharma space. And then we use a VP8 Modbus output as our standard connection. This goes along with, again, a lot of our pH and DO, as well as VCD conductivity measurements, as well as a decent number of other measurement pH measurement sensors. On the front end of the sensor itself, we have a fixed optical path length. This is 5 millimeters, and it is unchangeable. And within this, we have our stainless steel system, as well as sapphire glass window that is conformed to a smoothness standard, or it's conformed to a certain smoothness that allows for cells to pass through and the measurement to be made without occluding the measurement and or resulting in fouling on the front end of the tip. The Dencytee Arc measurement range is vastly improved from our predecessor product, and we now specify that you can get up to 200 grams per liter dry cell weight with this sensor as a single measurement. Other units that are often used to kind of specify this are 0 to 4 absorption units, or 0 to 30,000 NTUs. The measurement's done using a near infrared wavelength, and it's fixed at 860 nanometers. This is unchangeable, but also this was the optimal wavelength for us to remove any visible light spectrum contributions to the baseline signal, things from things such as media coloration and the like. In terms of resolution and accuracy, we specify a resolution of 0.05 grams per liter for the low end of the cell density range. We'll say 0 to 10 grams per liter dry cell weight. And then beyond that 10 grams per liter dry cell weight, we look at the resolution at a percent of the total signal. And so we'll say 0.5% for everything above 10 grams per liter. We specify a reproducibility of 1% sensor to sensor measurement. And you can test that for yourself with multiple sensors in line. And then where we also specify a high degree of reproducibility is in the linearity. And this is what we say when we are talking about trying to correlate against a offline standard. So offline, such as offline OD measurement. We say that all things equal, and if you utilize our sensor and its measurement parameters within conformance, you can get a linearity against your offline standard within 1%. That's not taking into account the inherent error associated with whatever measurement you're comparing against, though. And so what we have seen historically with transmission-based systems is that they perform very well at lower dry cell weights. However, as you start looking right here on the x-axis, as you start looking against really high cell density processes such as E. coli or large filamentous systems, you really start to get this saturation curve in terms of what the sensor can measure versus what the actual cell density dry cell weight is. By combining the reflection and transmission modes into a single output signal, the Dencytee Arc is able to maintain linearity throughout the entire measurable range here and doesn't suffer from that inherent saturation characteristics that we see in transmission-based systems as you get to the higher cell densities. The sensor itself comes pre-calibrated from the factory, and we have certificate standards that come with it so that you know it can measure a low and high range of measurement out of the box, and it's within conformity. So we have water as well as a 10,000 NTU standard that comes with the sensor itself, as well as the sensor being pre-calibrated from the factory. This sensor can handle pressure ranges from 0 to 12 bar and is CIP, SIP, and autoclavable up to 140 degrees C. So this sensor is designed in production environment to be in the side bioreactor wall and plugged in. And you don't need to remove it in order to SIP it. It's meant to be SIP'd in place. Now, the sensor itself will not operate and measure at 140 degrees C, but it can handle thermophilic applications. And so the operating temperature of the sensor is up to 80 degrees Celsius. So if you have a process where you run your cell line at 45 degrees C, 55 degrees C, the sensor measures and will measure just fine for that application. The sensor itself has a Modbus native digital connection off of it. However, we at Hamilton want our sensor to connect effectively to your process control system. And so we have a suite of conversion signal outputs to fit whatever your process profile and your process communication profile is. We have the ability to convert the Modbus digital signal to a 4 to 20 milliamp analog signal input if desired, as well as convert to other digital communication protocols such as Profibus, Profinet, Foundation Field Bus, and OPC UA configuration. And so these systems we already have for all our other ARC sensors. And so this really does fall in line with the Hamilton standardized ARC portfolio in terms of what the outputs are and what information can pass through. Now, what do I mean by ARC profile or ARC portfolio? Hamilton takes the stance of you don't need a transmitter in order to get an effective measurement. And so we built our ARC platform around the idea of transmitterless technology. And what that means is when you look at a Dencytee Arc sensor and you want to make a TCD measurement, you don't need a sensor paired to a transmitter, paired to an output card, paired to something else in order to get a measurement signal. In order to get the actual signal itself, you really just need the Dencytee Arc sensor. And so we built in the transmitter into the sensor head itself. And so this is an all-encompassing sensor measurement plus signal conversion into Modbus digital. And so at its core, if you want to make a measurement with this, you really only need a sensor and a cable at bare minimum. Now our sensor has a built-in transmitter within it, and this includes space for configuration parameters as well as configuring the measurement profiles of the sensor itself. And so in order to pair and communicate with that, you can do it digitally via Modbus, or we provide a ArcAir free software package that allows you to directly communicate with the sensor and make the desired changes in the configuration profiles. And those profiles they are saved and persist within individual sensors themselves. So if you've used any of Hamilton's previous systems, Hamilton ArcAir 3.5 or 3.7 is the current version that has Dencytee Arc support added into it. So if you've used this with an inside Arc system and want to try out a Dencytee Arc system, hop on our website and update to ArcAir 3.7. It's free, and you'll be able to hook up a Dencytee Arc sensor and see it on your dashboard. So within ArcAir, you can configure things such as the measurement settings, things such as moving average, filtering, measurement interval, as well as the configurable units that you want to output. And I didn't mention it earlier, although it was on the slide deck. This sensor has the ability to output signals in pack cell volumes, offline OD, CFUs, cell dry weight, cell wet weight, even cells per mil. There's a very large swath of measurement units, as well as measurements that can be correlated against with the Dencytee Arc sensor in order to get that value in real time. In addition, the sensor itself, you can configure communication settings within it, as well as if you really want to, you can also validate that your sensor is within conformity. So we have those abilities to essentially confirm that the sensor is configured properly for connection to your process control system. The sensor is intuitive in the sense that you can either manually count cleaning cycles if you do something such as an autoclavation, things for tracking, say, the lifetime of the sensor, as well as if the sensor is connected in process and it's powered on, it'll actually count when it undergoes a CRP or SIP cycle based upon temperature time profiles that you can define as a user. And then everything from the sensor, it can be reported. It's all documented and all able to be exported in a PDF file. So there's no need to say what was the actual sensor setting or how many operating hours did it have at this point in time, you know. And then if you really want to take the sensor and just start working with it and see, hey, does it give me a good signal? How can I use this? Use ArcAir, use a cable, use our sensor, and put it on your put it in your bioreactor area, and you can collect data using experiment tracking within ArcAir. In addition, within the sensor itself, we have an offline correlation mechanism, and this is an important component to use if you intend to use the multi transmission reflection output mechanism for this. Essentially, the sensor will allow you to translate a value that you have in your bioreactor at a given point in time into, it'll essentially correlate against it and output that signal. Now, why it's important is you need to tell the sensor, at the certain points in time throughout the duration of the fermentation what value it should be expecting, and it's going to use a combination of the transmission and reflection values it sees in order to get a single output. And so with this kind of mechanism, we've seen that we're able to really maintain linearity throughout the entire process because we're using varying extents of reflection and transmission rather than just relying upon a single value output for this. Now, this process right here, this offline correlation, you build it within ArcAir, and then you can essentially output it as a reportable value and leave it as a fixed model within a sensor. And so to that extent, we say it's useful for GMP processes because you define it and then you set the parameters and it does not change. Now we have ArcAir Basic. If you are interested in using this system in a GMP style environment, we have something called ArcAir Advanced, which is essentially the paid version of our free software that includes all the verification, audit trail reporting, as well as documentation functions that you'll need in order to have sort of the quality batch records you need for this particular sensor in a GMP environment. As well, if you want, if you need on-site support, we can offer a IQOQ qualification package as part of the GMP conformance for you. As well, we have a specific maintenance kit for validation, verification, as well as recalibration of the sensor periodically. We've undergone and replaced the liquid standards with these solid state components for various reasons, but just know that when you buy a maintenance toolkit, it stays with you for the life of the sensor. Now let's look at a couple applications for Dencytee Arc. So the first one I want to point out is something early on in the process. Let's say you have a process where you need to induce or a fermentation where you need to induce. Historically, this would have been done by taking offline samples if you're looking for a specific density or a specific TCD value in order to induce at. You would take a series of grab samples in order to try and find this specific value. And this is cumbersome, time consuming, and while you can get pretty close, it's technically speaking imprecise. Now, if you include an inline TCD measurement with, say, a Dencytee Arc sensor, you have a signal that's continuously output, even on, say, ArcAir from the experiments tab, and you can look at that value at any given point in time, and you'll know exactly when you hit your specific TCD density to make your induction point. In doing this, you can be more consistent and be more precise. And so with this, we'll say that it improves your timing when you try to make these critical process points. And it's applicable for low cell densities. So this sensor really is, if you can measure it with offline OD values, you can measure it with our sensor. With this, we hope to reduce manpower, reduce that sort of iterative guessing as you get closer to a critical time point, and then release manpower. So if you have 6 bioreactors in parallel doing this, you don't need to take 4 samples. You can take a confirmation sample via offline once you achieve your target TCD value on the Dencytee Arc. And overall, this should increase efficiency, improve reproducibility within, say, process development, as well as just normal day-to-day operations for a particular fermentation profile. So let's look on the other end now of a fermentation, and let's look at the harvest point. So we have the same thing here with our offline OD values. Now, historically, for very high cell density processes or high cell density processes, let's say E. coli, high cell density E. coli processes, you want to try and harvest at a specific time point, and any inline measurement that runs on a single measurement principle typically becomes semi-saturated, as we showed with the transmission only modes here. And so while you can use this historical signal for early phase process action, it really sort of falls short on the upper end here, specifically say during harvest point. If you use the offline OD correlation tool and combine measurement modes, you can get high linearity and correlability and correlation against offline OD throughout the entire run. So you can use the inline OD sensor for endpoint determination as well as early phase. And the point here is there's no need for a single sensor, or there's no need for a dual sensor, multiple sensors, or multiple models based upon the linearity during certain ranges. With Dencytee Arc, a single sensor will be applicable for the entire measurement range. And what we want to do is we want to empower you to have higher precision for these critical process events, as well as lean more on the inline measurement itself, and trust that that measurement is true. So we've talked about looking at values and making a determination. The other thing that an inline signal provides is the ability to automate. So offline OD values, you have to physically take the sample and make the process change on your own. With an inline measurement, the signals continuously output in a variety of communication formats, and it really enables you to not only remove that manual aspect, but automate it and allow, remove the manual aspect, but also add redundancies, relays, flags, alarms behind the system. And so an example here would be you can automate the target TCD required for harvesting and then perform something such as perform the actual harvest action, or perform, say, a bleed system in order to remove a certain product. And so it's not just for harvesting. You can automate induction as we pointed out earlier, and you can automate feed control, or even you can automate sort of bleed control, thinking more in a turbidostat configuration for fermentation profiles. And so at the end, and I'll summarize here, Dencytee Arc, what we really want Dencytee Arc to be for you is we want it to be a real-time measurement that you can trust, that will enable you to have process control, not require many components in order to integrate, and not require bulky transmitters as well as multiple conversion steps. It's a single sensor, it's a plug and play system. And then we want you to have an expanded measurement capacity, 0 to 200 gram cell dry weight. And we specify this to a high linearity and a high reproducibility. And then our hope is that with all of these benefits, your overall operating costs will reduce, and you may even increase your yields on your overhead for, say, improving your yield profiles. But at the end of the day, we really want you to reduce operating costs and increase efficiency, because your time is money. If you're interested in the sensor or reading more about the specifications, we have a dedicated page on our website at hamiltoncompany.com/dencyteearc. Or if you want to start a conversation, we have local area sales managers throughout the world. Yeah, please feel free to reach out to one of them. If you need help finding your local area sales manager, we have a location on our website that'll give you the appropriate person to contact. The appropriate person to contact. And so with that, I'll say thank you for your attention. And I'm going to go ahead and wait about a minute, and then I'll open up to questions. So yes, thank you. And if you have questions, please feel free to put them in the Q&A section in the corner here. I'll start compiling them and look at them. Okay, I will get started. We have a couple questions here. So the first one is, does Hamilton offer a demo program for the Dencytee Arc sensor? If so, how do we get a demo? The answer is yes, we do offer a demo program. And in order to execute upon that, you'll need to get in contact with your local Hamilton area sales manager. They can help walk you through the steps, what is to be expected, and how we sort of undergo our process. So yes, the answer is we do have a demo program, and we have a data analytics team that supports that as well. So the best thing I'll say is contact your local ASM, and if you don't know who that is, feel free to reach out. The second question I have here is, to which extent is the TCD signal affected by interferences based upon air bubbles, liquid droplets, and solid particulates? So I'll break those apart into different discussion, slightly different discussion. The air bubbles, typically high aeration, will impact the signal quality of a Dencytee Arc sensor or of an inline TCD measurement. The reflection mode coupled with the transmission mode actually does a pretty good job at reducing the, I'll call it the signal to noise ratio increase, or the ratio of noise on the baseline signal behind it. So to that extent, the Dencytee Arc sensor does pretty well with air bubbles. So I would not worry about, say, various varying aeration profiles and such in terms of impacting the signal quality itself. You still should be just fine. Liquid droplets, defoamers, will typically not impact the sensor unless you, say, have had an anti-foam dump within the process, and at which point there may be a slight filming on the through the measuring pane of the Dencytee Arc sensor. But in any typical application that's not a corner case, process failure, or some very extraneous situation, defoamers work out just fine. There should be no problem with that. Now, solid particulates, on the other hand, will impact the measurement itself. So you can think of a particulate based upon its size will diffract a certain fraction of signal. The larger the particle, the more the signal will diffract. So if you have a system that has significant amount of solid particulates, that system you might want to assess, is it applicable for an inline OD measurement, because it will impact the baseline signal itself. Let's see here. Will these slides be made available? We will put this this webinar or a variation of this webinar up on our Hamilton website for you to freely review. And so the answer is no, the slides will not be available, but the webinar will be. Let's see here. Let's see here. Sampling a bioreactor for offline measurements is invasive and leads to smaller pools of data compared to PAT sensors. Besides the applications you have shown, have you seen examples where cell growth kinetics or cell growth parameters would be significantly different between the two approaches, offline via online cell concentration, leading to differences in process conditions and target product productivity? So that's a full question. Thank you for that question. The answer to that one is I've seen offline. So typically what I'll find is offline based measurements being discrete in nature, you typically will only update a control parameter n number of times, where n is the number of measurements you're taking and recalculating. So let's think of something like specific growth rate. If you want to do a exponential feed profile using a base feed, or not a base feed, using a pump system, and you want to modify the pump speed, typically you'll find the discrete nature, you'll just have steps where you've manually adjusted it. Inline control systems, I've seen they'll continuously adjust, and if we think about the big picture on that, you're adjusting to the dynamic nature of the cell population itself. And so in theory, and what I've seen in practice in certain papers, is that you'll get higher productivities from this because you're continuously addressing a dynamic nutrient feed requirement for a particular process. So that being said, if you have a well-defined system with offline OD measurements and you build a kinetic model around offline OD measurements, and that model is consistent, then that model, if it's implemented in sort of a static nature, can perform comparably. But I would look at individual applications on that. What's involved with integrating this probe with a process controller for automation? Is 4 to 20 milliamp output the easiest / fastest way? The answer to that is it depends upon your system. Typically, if you want to hook this up to a bioreactor, you have to have the 4 to 20 milliamp input available, but that is probably the fastest way to get a signal into a bioreactor. On the opposite side, the sensor itself outputs a single measurement or a single OD value. However, the sensor itself has a significant amount of additional data, as well as some of the raw data on the back end of the sensor that's available only via digital protocols. So if you want to just get the sensor hooked up to start collecting and build a PID loop, 4 to 20 is the way to go. If you're thinking more, you want some of the PAT tools, additional data and information, digital's the way to go. And then if you don't want to mess with integration at all and you just want to collect and monitor a profile, there is no problem with just using ArcAir and collecting via experiments. I actually recommend that if you're kind of questioning, do I really need this data? How useful is the data? Do a proof of concept. Just collect the data via ArcAir and do a proof of concept. It's a free software. How does the system compare with the 90-degree turbidity system when measuring NTU? I actually cannot comment on that. I'm not sure about the answer on that one. My assertion would be if the 90-degree NTU system has a high degree of linearity throughout the duration of the process, then I would say it's going to be comparable to our measurement parameters. If there's certain caveats to the 90-degree turbidity system, then those caveats might not be reflected in the Dencytee Arc system. Yes. So yeah, sorry, I can't fully answer that one. I don't have too much experience with the 90-degree turbidity system. In Dencytee Arc, preamp versus version absorbance is measured, but Dencytee Arc seems to measure both absorption and reflection. Does the advantage of this serve to increase the measurement accuracy? The answer to that one is it doesn't necessarily increase the accuracy, it increases the measurable range. So typically high cell density processes, a reflection-based system will do better at capturing the linearity if you're trying to correlate against something. Whereas reflection-based systems may suffer from some inherent resolution issues on the low end of the concentration. So the main thing is we've combined the measurements to increase the measurement range where the system is linear, and by extension, that increases the precision of the system as well as the what we'll say is the overall accuracy, because there's less point-to-point variation that we could expect from various TCD/biomass profiles. The wavelength has been changed from 880 to 860. Is 860 more effective? That's a bit more on the proprietary side of our systems, but I'll comment that both the legacy system as well as the current system both assess 880 and 860. But I can't tell you exactly what the difference is in terms of effectiveness and profiles. They're fairly close and they're both near infrared. So this might just be more of a design change. And I'll leave it at that in terms of hardware. What applications are preferable for the Dencytee versus the Insight probe? Thanks. Good question. So Dencytee is very good for most fermentation profiles. Fermentation profiles where you have lower cell concentrations, you have to really look and assess, is an inline capacitance sensor applicable for it, or will the signal response be too low for the process? In systems like that, density is clearly the way to go based upon concentration limitations. As well, depending the type of process, you may see varying signal to noise ratios on a capacitance sensor versus a inline OD sensor, at which point you want to compare if you want to, depending upon your level of automation capability and signal processing, you may want to go with simpler is better, and that could be either or based upon signal quality. But yeah, typically bacterial processes where you don't have super high cell concentrations, talking, high cell density E. coli processes are great for insight probes. But if you don't have that, you may want to look and say, am I in the applicable range for the insight probe itself? Do you see any advantages to combining the information from this sensor, live and dead, with capacitance, only live cells? Could these sensors give you a combined read on viability? The answer is absolutely yes. So that is one of the ideas we wish to push, and the ideas we are pursuing is that if you have a measurement of TCD, that is VCD plus dead cells combined, and then you have a measurement of VCD, that is viable cells only. With the proper model building, it is very much within the realm of possibility to get a estimation of viability throughout the duration of a run. So to date, Hamilton does not necessarily provide that as a complete solution, but if that's something you're interested in, talk to us. We definitely have experience on it, have ideas, have models that we're working with. And so our data analytics team would be more than happy to have that conversation. Cool. I think that's all the questions. Good questions, everybody. I appreciate your time on it. With that, I will actually say we're going to close out the webinar. If you have any outstanding questions, thoughts, or you just need to connect, my email's at the bottom of this, at the bottom left of this webpage. And yeah, please feel free to reach out. I'd be more than happy to answer any additional questions you guys have. Cool. And thank you. With that, I'm going to go ahead and close the webinar.